All right, we are looking at angle bisectors and their relationship in triangles today. So the first thing we're going to do is look at the angle bisectors. These ones you do not need to do on your own. You're just going to follow along with me. So you can follow, or you can do them on your own if you would like to. You just don't have to. So the first thing we're going to look at is the angle bisector. So I'm going to draw an angle here. This is angle BAC. And kind of like we did before, we have our construct tool, which allows us to bisect an angle, select 3 points or 2 lines. So I'm going to select the 3 points here, and I get my angle bisector. I'm going to put a point on the angle bisector here, and the question for us then is, what seems to be true about this point on the angle bisector? Well, this might be a little bit difficult to see, but if we remember back on how we take distance from a line, or in this case a ray, to a point, it's the perpendicular to that side. So if we pick a point and the line, we pick a point and the line, we get this, and I'm going to put points at the intersections here and here. So the distance from the ray AC to D is the segment DF, and the distance from the ray AB to D is the segment DE. And if we take a look at that, we find that DE and DF have the same length, right? So if a point is on the angle bisector, then it must be equidistant to the sides of the angle. And if we move anything, right, if we make our angle bigger, we make our angle smaller, those two things work the same. So a question we might ask is, how do we know that's going to be true? Why does this work, right? Well, if we clean up our diagram just a little bit, we can kind of get a better picture of this. So I'm going to get rid of these. Now I'm not actually getting rid of them, I'm just kind of hiding them here so that they're not in our way. And then I'm going to draw in segments here instead. And what this does is it gives us a better idea that we're just looking at two different triangles, right? We're looking at triangle AED, and I might just get rid of B, throw it up there, and we're looking at triangle ADF, right? And what do we know about these two triangles? Well, if we do a couple of more measurements, like, well, what was E? Well, E had to be perpendicular because that's how we find distance from a point to a line. And the same would be true for DFA. They're both 90 degrees. So we're dealing with right triangles. Second, we drew in the angle bisector. So this angle has to be bisected. Right, so these two angles down here are the same. And we also have the reflexive property telling us that AD is congruent to itself. So we have the hypotenuse of both triangles and an angle. So hypotenuse angle tells us that these two triangles must be congruent. Therefore, by CP/CTC, the measures here must be congruent. Now note that this is true primarily because this is a right triangle, right? However, in all honesty then, if we knew that the angles here were congruent, that would probably be enough for us, right? So again, if a point is on the angle bisector, then it must be equidistant to the sides. Note that to have the true distance to the sides, then it must be perpendicular to the side. The converse of that would also be true. That's the Angle Bisector Theorem and its converse. Now, how does this relate into a triangle? So let's draw a triangle and draw in its angle bisectors. So polygon, we have a triangle. To measure an angle, we have construct angle bisectors. And this time I'm just going to use sides. So bisect, that does not work. All right, so I'm going to use angles, points. So I got an angle bisector of A, angle bisector of C, and an angle bisector of B. And note that they are concurrent. They meet at a single point in the triangle. This point of concurrency, D, is called the incenter. Point is called the incenter. And, well, what does it do? Well, if D is on the angle bisector of A, it must be equidistant to the sides of A, which are AC and AB. In other words, again, this gets a little bit messy as we put stuff in. So I may go back and clean it up a little bit. So if I looked at the perpendicular line from C to D, and if I looked at the perpendicular line from D to AC, and if I look at the perpendicular line from BC to D. Like I mentioned, this gets a little bit messy, partially because some of the lines here are currently crossing each other. Right, so what I'm going to do is I'm going to hide my angle bisectors for now. So the point is still made. That's not the one I wanted. The point is still made up of the angle bisectors. However, I've just hidden them so that we can look just at the other part. Right? So again, I'm going to mark my diagram with these points. And we said that if it's on the angle bisector, then it has to be equidistant to the sides. So since D is on the angle bisector of A, DE and DG must be the same length. Well, let's see if that happened. DE and DG are in fact the same length, as is DF. Right, so all three of these segments to the sides are the same length. Again, this is called the incenter. And these measures are just kind of getting in the way, but we'll deal with that. So this is called the incenter, and what you can do with it then is draw a circle that touches each side exactly one time inside the circle. So the incenter is inside the triangle, drawing a circle inside the triangle, touching the side of the triangle once. And again, that makes sense because then each of these distances, D, DF, DE, and DG, those segments are radii. Now, where can the incenter happen in a triangle? Well, this one's easy, right? In an obtuse triangle, it's inside. In a right triangle, it's inside. And in an acute triangle, it's inside. So the incenter is always inside the triangle. Incenter is always inside the triangle.